So where do all of the electrons go in cellular respiration? If you have glucose, which is C6H12O6, you should know this. And we're going to break that down one carbon at a time. It's going to give off a lot of energy that we need to store. But to do that, when we break bonds, we've got to deal with moving electrons. Every dot you see on this chart is an electron being reduced or oxidized. So the movement of electrons between different compounds. Now please do not try to memorize this. But what we need to look at and what we need to think about is, why would your cell go through all of this mess for glucose? And the idea is this slow, methodic process allows us to be much more efficient. You are about 40% efficient, we said before. So you get about 40% of the energy out of glucose that's there. That's amazing. It may not seem great. You might not want a 40% on your exam, but 40% efficiency in this energy transfer, doing things this way, is amazing. So glucose is actually going to lose hydrogen atoms. And if you lose hydrogen atoms, you're also losing electrons. And if you're gaining hydrogen atoms, you're gaining electrons. Why? Well, if I make oxygen more negative, what does it want? It wants hydrogens. So we look at, it's easier to look for where hydrogens have moved to than it is to look at where electrons have moved to in these kind of reactions. So if glucose is losing electrons, it's oxidized, right? And if oxygen is gaining electrons to give us water, oxygen is actually reduced. So glucose, oxidized, oxygen, reduced. Some of you may know Leo the lion goes grr. Lose electrons, oxidized. Gain electrons, reduced. Okay? Just to help you remember. So in this process, we need a couple of players in this game. One major player is dehydrogenase. Well, you should know what ACE is now. ACE is an enzyme, right? So it's going to help us actually start to break down our glucose molecules. And dehydrogenase in particular breaks off hydrogen molecules, or hydrogen atoms. So when we do that, when we break those away from the organic molecule of carbon and hydrogen being glucose, we can start to break down things pretty quickly. NAD+, this is, please don't remember the name. I don't care about the name. NAD+ is fine. And what we're going to look at here is this is actually an enzyme that is going to transport or move electrons. So I talk about this as the electron taxicab. Its job is to pick up electrons, drop them off. Pick up more electrons, drop them off. And we see this all through the process of cell respiration. So it's going to pick up electrons. Here's our NAD+. Pick up electrons. When it picks up electrons, it becomes reduced, the charge goes down, it becomes NADH. Why this H? We said if you add electrons, you're going to add electrons, now NAD has a negative charge, it wants to pick up hydrogens. So this process allows us to move And what we're going to see is allows us to move these electrons efficiently around your cell. Because if you break bonds and release electrons, they're not well behaved. This is like herding cats, okay? So we've got to get these electrons moving in the right direction because we actually are going to build a concentration gradient using electrons. So here's my little taxicab for you to show you the movement, and we're going to pick up electrons and then drop off electrons someplace else. So these will be important players for us in this entire process. In particular, we're interested in NAD+ taking electrons to something known as the electron transport chain. This is where we're going to see the majority of the ATP built inside your cells. We will come back to this, but I want to show you the players kind of in place. So the NAD is going to pick up electrons. It actually does this in the cytoplasm of your cell. And it's going to transport NADH with the electrons, is going to transport those electrons to the electron transport chain, which is in the mitochondria. So while the mitochondria is central to efficient energy conversion, it is not the only place we see things going on with cell respiration. Okay, so next we want to look at what are the actual stages of cell respiration.